muscle strength. And I think that that's the same with the exoskeleton device as well. So it's just also, with regards to this, I was just putting this together a little bit, but I've not finished it yet. This is Scott Summit. So he is the founder of Bespoke Innovations. So it's part of 3D Systems now. And the idea for him originally was to turn something like this, which is doesn't give people significant self-esteem and confidence, to this, where the lady here is kind of using almost proud of this, we've had a couple of discussions over the last couple of days about scoliosis and spine curvature, and this is Scott's current project. And actually, let me. So this is what he's kind of working with. Let me see if I can actually find. Oops, lost it. That is a scoliosis brace. That's what he's kind of working with. Imagine giving something like that to a 14-year-old girl. And so this was his motivation, because if I had my daughters at that age, if they were asked to wear something like this, I'm sure that they wouldn't. And if they did, they would be severely traumatized psychologically. If they're going out to school and things like that, wearing something like this. But compare that to this. Let me blow this up a little bit so you can see it a bit easier. So this is actually forming the same function. So we looked at consider the exoskeleton. It's got spring devices in there, essentially using the elasticity of the nylon during the 3D printing process, creating long deformable pathways, which essentially is what a spring is. So you can create quite significant elasticity within the 3D printing process. And so he's taking advantage of that, and the fact that you can control the elasticity by changing the amount of the density of the material and the directionality in which all of these springs go. So if you can look at this a little closer, you'll see that there are some solid regions which are essentially stiffening, which gives you the support, and then elastic regions where the person can move naturally. And so, but that spring pressure is helping to push the spine into a straighter mode. Every condition will be somewhat different, the uniqueness again. So this has to be designed specifically for this patient. The previous design it's by adjustments. You know, you adjust a strap here, you adjust the spring strength there, and you get that bracing effect. Here, because you don't need to adjust it, it's because it's designed, or you don't need to adjust it because it is designed in a way that is specific for this individual. So the force, it's already adjusted, it's pre-adjusted, if you like. Okay? Now, it doesn't work for all scoliosis conditions. There's a thing called the Cobb angle, which basically defines the amount of curvature in the spine. It's not a very precise measurement, but it's a way to determine the severity of the condition. These kinds of braces are designed for low Cobb angle, i.e. not very deformed conditions. I showed a couple of examples of the work that some of the work that I'd done with a spine surgeon, where you put these rods into the spine. You actually surgically implant them as a way to really force the spine and to support the spine during its remodeling process. That's not what these braces are designed to replace. Currently, there is no better solution for severe Cobb angle correction other than surgery. And but there are even there methods that we're working on. For example, there's a lot of effort in the use of shape memory alloy to provide the straightening strength. So building the rods from an SMA, which basically are set in one condition at one temperature, but then when you have it at room temperature, it's trying to straighten out, which is then applying that force onto the spine. But these things are extremely complicated problems. Even this, I think, is a pretty complicated problem. You cannot design this kind of brace, this kind of jacket, without significant consultation with a clinical specialist in scoliosis. So, you know, I mentioned previously about people doing stuff that maybe isn't sort of verified and ratified by medical councils and the like. That's not the case here. That all of these designs are then performed and created in conjunction with clinical specialists. Anyhow, looks like most people are here now. So let's get on, because I know some of you, quite a few of you are kind of waiting. Let's get rid of him. Bye-bye, Scott. Oh, just, yeah, show you that one as well. These are some of the other examples. It's kind of, it's doesn't work very well if I show these slides in the wrong order. But the intention of this slide was to say, okay, you've got three images here. Are you able to work out what the similarity between them is? And obviously you know. But I just kind of wondered whether, when you look at this, if you were to look at this at the first time, would the first thing you would consider is that all of these people have an artificial limb? And that's Scott's intention, really, to divert you away from the obvious, which is what a lot of designers try to do, and to bring you into another viewpoint. You know, you don't have to think about, you know, you might look at this one and say, oh, that's a nice bike. Or you say, this is a pretty lady. Or this guy's playing football, without realizing that this is an artificial leg, this is an artificial leg, and this is an artificial leg. Anyhow, okay. Now let's get rid of it. Yes, and I'll save that. Okay. Oh, and get rid of that one as well. Never mind. Right, what I wanted to do was, oops, come across here. All right, bioprinting. So although I've worked in this domain, I work in this as an engineer. Okay, so it's important for me to understand what people need in this domain, but a lot of the complexities, particularly around the biochemistry, I can only describe in layman's terms. All right, so this is my disclaimer at this stage. All right, I know a lot about additive manufacturing. What I don't know a lot about is tissue engineering, or bioprinting if you want, in this context. Somebody who knows a lot more about it is a good friend of mine. His name's David Prof. In fact, he's a associate professor at Colorado State University. And I'm actually quite proud of the relationship with David. I was at a conference. Dave Proal is a friend of Terry Woller's. He's a computer scientist by profession. Made a lot of money in the early days developing software tools, and spends a lot of time talking to people about software security. And he came along to a conference with Terry in Portugal, mainly because he likes Portuguese wine. And so I was talking to him, and he was sort of saying, all right, you know, he's very interested in all of this. He knows a lot about what Terry does. And he said, you know, and he said he'd come to a conference like this, and he says, it makes you want to go back to school and study for a PhD. And he was about 50s, mid-50s at that time. And I says, well, why don't you? And he said, well, yeah, I'm too old for that. Why should I want to do that? I says, well, yeah, I said, that's not a good reason, not a good excuse. Why don't you actually get a PhD? So I actually encouraged him to do a PhD. He did it. He then, in the process of doing his PhD, he set up a lab in Colorado State University. He got a faculty position pretty much straight away, and he's been spending the rest of his life, the remainder of that time, working in this area of bioprinting. So, yeah, I kind of feel that, yeah, I had some input on that. I'm quite happy with that. Very smart guy. So, this presentation is an adaptation of a presentation that he gave, and I asked if I could borrow it and use it, and he said yes, not a problem. So it really hopefully addresses a number of the issues around bioprinting, tissue engineering. And it reflects a lot about, in some ways, about what I've been telling you in recent in the last couple of days, that at the moment, bioprinting, the majority of bioprinting is not focused on printing organs for implantation. Okay, there's a lot of speculation and there's a lot of effort being devoted to achieving that, but the majority of it is more in this kind of space. Research. So the need for surrogate tissues, the need for artificial, if you like, tissues, artificially generated, not harvested from humans, for research development and testing. When you do work in this space, you find yourself having to work on the bioactivity of the work, you know, of the materials and systems, drugs, etc., that you're working with. So you can do animal testing, but we all know, I mean, the animal testing isn't necessarily the same as human testing. There's also a lot of issues around animal rights, and therefore, if you want to do animal testing, you really have to justify to the nth degree that it's the only or the best way to do that kind of test. So there's a lot of pressure to try and create other means for doing all of this testing. And so this is where the majority of effort currently is located. Some of it is just in a sort of a self-fulfilling purpose that you're doing test models in order to understand how the cells grow so that you can then eventually create the tissues that are suitable for implantation. So it's sort of like, in this case, a product design process, you know, an iterative process. You know, if you want to make parts, you want to design something, you've got to iterate on that until you come up with something that you're satisfied with, you know, from all of your specifications and objectives. It's the same thing here. You want to make a tissue, you find that it's not got the right formation, so you make it again. It's not got the right complex structures, so you'd make it again. So you work on how to adapt and develop these tissues. So development and testing. Live subjects are expensive and difficult, complicated in terms of the approvals and etc. And obviously, you know, if you want to do experimentation on live subjects, you've got to think about the welfare of who it is that you're experimenting on. Okay? So this is where a lot of the scaffolds that we keep referring to are being used as test subjects, sort of like a lab-based experiment. So very Frankenstein-y. Having said that, there's a lot of different directions in where people are going. And so we mentioned about the ASTM standards that I've mentioned a couple of times, and I said that there's quite a lot of discussion on terminology. So it's not just about the terminology of what the 3D printers should be called, it's also in terms of the domain in which these printers are being used. So these are some of the terminologies that are appropriate to the area of bioprinting. So we recognize some of them: photopolymerization, binder jetting, powder fusion, and sintering, inkjet printing. But then we also note that within the ASTM definitions, there's also reference to cell, tissue, and organ printing, okay, to scaffolds, and to bioinks. So these things are all within that realm as well. So bear that in mind, that ASTM is not just about the technologies, but also in terms of the domains in which those technologies are being applied. So I can imagine if I wanted to do a similar thing for aerospace, I would probably see quite a lot of terminologies there which are appropriate to aerospace, which ASTM understand either through other definitions and other domains, other standards. Okay? Another one at the top there, which I haven't mentioned yet, viscosity printing. So this really relates very heavily to the bioprinting domain because we are very often using bioinks. So one of the things we might sort of look at is what is a bioink. Another thing to bear in mind is that a lot of this have actually come from this sort of original low cost. So it's funny, you know, medical research is probably the most important research that we can do on the planet, but it's very commonly not done because it's not very well funded. So it's interesting to say that we have much more, we put much more importance on weapons research and destroying people and planets, less importance on trying to treat the organisms which are resident on that planet. But that's just me speaking, okay? All right, I'm on record as saying this, all right? So I don't know if I'll ever get to be a politician. But one of the things, again, I relate to this thing about technology convergence and the fact that technologies now are so much easier to access and so much cheaper. This is having a significant impact in the research domain. Okay, so you guys have never had it so good. You know, if I go back to when I was doing my research, when I was doing robotics, and I wanted to, I spent a lot of time building end effectors on industrial robots. And I would design these things, I would draw them out by hand because we didn't have CAD systems. I would then have significant and lengthy discussions with the technician as he tried to understand my drawings. He would then start to essentially build my design, but keep coming back to me to check, is this what you actually wanted? So that we could ensure that he didn't make too many mistakes. And then I would eventually, and then I build and equip it with the sensors and the cameras that I had and carry out my research. So one iteration on my design probably cost me a month, maybe more. Okay? Because this guy was also very busy with other things. Now, if I want to iterate my research, if I want to build end effectors, I can do it within a day or so. Okay? Even in doing the design and everything. And it's largely because of this guy here, or this item here. This is the original RepRap machine, referred to as Darwin 1. Okay? Adrian Bowyer, the inventor of this thing, his vision was what was called a von Neumann machine. Anybody understand what's meant by a von Neumann machine? No? Okay. You know John von Neumann. Okay, so he's a German mathematician. Yes? All right. So he had this idea and actually proved it somehow, I don't know how, that it was possible for a machine to replicate itself and, in the process, improve itself. Okay, so it's sort of like an artificial evolution. And so the concepts there were about, tolerances and precision. So what he was saying is that it should be possible for a machine to create something which would have a higher tolerance than it itself was functioning at. Okay? Interesting concept. Worth looking up. So this is sort of, that's why Adrian called this the Darwin machine. Okay? Because he basically is saying it's a sort of a crossover. And if you look at it, the reason behind why he was calling it the Darwin machine, you look at a lot of these components here, and you actually look at a lot of 3D printers today, you'll see that a lot of the components on the machines themselves are actually 3D printed. And that's what he was trying to say, that 3D printers could print themselves. Okay? And that also led into research into things like bioinks. But before bioinks, it was also leading into research, and it's the sort of stuff that you're doing, where you're making and 3D printing sensors and actuators. because, yeah, you can make the devices and the structure and the mechanical mechanisms quite easily on a 3D printer, but what about the other aspects, the device, the sensors and the actuators? So a lot of people are then also driven in that direction, and it'd be quite interesting for people to look at that too, if you wish, as a research direction. I think it's a great one. What is this form of not just embedding sensors into structures using 3D printing, but also creating those sensors and devices within the 3D printing. Eventually this is going to happen. It's just a matter of being able to understand and be able to manipulate a sufficient number of materials. Okay? If you look up on the websites, you look at also a variation of RepRap called Fab at Home, F-A-B at Home. Another at home. This was a project which was initiated at Cornell University in the US, particularly Professor Hod Lipson, who is quite well known in this arena as well. Hod Lipson. If you look at some of the early work on there, you'll actually see that they've been able to build some actuators. There's a very interesting video where he used the Fab at Home to build a battery. So not only sensors, actuators, but also energy sources. So it's possible. It's not a very nice battery and it's not a very powerful battery, but it is a battery. So long as you can make somehow deliver the materials, so you just have to deliver some materials which react together and create electricity. Okay? Anyhow. Sorry, say again? What is a lithium-ion battery? No, it's a silver nitride battery. And what it is, if you look at it, so you have to put the battery in a casing. So he had the Fab at Home extruding, so he mainly used silicon rubber, air cure. So he used to extrude that, and that would create the casing. And then what he would do is he would deposit layers of silver nitride paste, which then would be sufficient to sort of create current. It's a concept, okay? I suppose you could do, probably the most sensible would be what's the LiFePO batteries, lithium, potassium, ion batteries. Those are probably the most likely ways to create batteries using 3D printing, I think, because you've got more control over the materials. Anyway, I'm digressing again. The Darwin machine has itself evolved into machines like this. So this is, if you are in that sort of bioengineering and you're wanting to look at 3D printing, tissue engineering, then these are the kind of printers that you might like to consider. When I started looking at this, there were no printers which were dedicated towards medical, so we built our own. But quite quickly there came the bioplotter from a German company. Got something tech in its name. Envision Tech. So Envision Tech also do DLP machines, but they also did a machine called the bioplotter. And that's actually very similar to this one. This is the RegenHu machine. Basically, if you look at this, you can see a lot of features which are quite useful in the bio plotter thing. Let's just go back a minute to this one. This one is from Cellink. It's a little unclear as to how this works and what functionality it has. But if you look at this one, you can see there's a lot of features in here. First off, in bioprinting, it's not necessary to have a machine which is really big, okay? Nobody at the moment is very interested in creating large scaffold and cellular structures. Most of the samples and things that you want to create are like a centimeter cubed, okay? So that's the first thing. So you don't need a big machine. Secondly, you don't need a very accurate machine either. So the drive systems and things are not that critical. In this case, you can see the drive systems are actually pretty good. You know, you've got a couple of linear pathways here, which are quite effective. Yeah, so we get that way movement, and we get that way movement, and we get that way movement. So it's 3-axis that way. Another thing to really bear in mind is that when I talk about not having a large platform, in particular, you don't really need much Z movement, vertical movement, because quite often you're just making, as say, things which are very, very small in height. You may find that you want to do a lot of these in some kind of biochemistry assay, you know, a sequence of experiments, and therefore you might have a number of cells that you want to work with, and so X and Y is probably more important to have a bit bigger than in Z. What is quite important is that you want to be able to deliver more than one material. So you can see here multiple heads. This is very common on a bioprinter. So having 4 heads, having a carousel system where you can collect the heads and deliver them, that's very common. However, the material delivery, you see it's not necessarily continuous. These are probably pneumatic tubing, not material delivery tubing. This is most likely, so you can see here, there's a colored ink in here. This is not colored. So what you're doing is actually just delivering some pressure to feed a syringe. So most commonly is that the material delivery is constrained by the volume of the syringe. Okay? So you don't need large amounts of materials. Say you're building small samples, probably those materials are very difficult to formulate, you know, because they could be in all sorts of chemical sequences. Who was I talking to yesterday? Where's the bioengineers? Sitting at the back, is it? Where? Lost them. Don't seem to be here at the moment. They were asking me about, you know, what's the best kind of scaffold and things to work on, and we were then discussing about scaffolds and the fact that, you know, saying, well, you know, they were talking about bioinks and preparation of bioinks with scaffolds, and what we realized and what we discussed was it's usually a very lengthy sequence of steps. When you build a scaffold, probably the first thing that you do is actually you then work on the scaffold by cutting it up. If you are using if you're building a scaffold, you probably build it like this for one layer, and then on top of it you'll build another layer. Okay, and then you've got sort of areas which are your volume space. Anyway, if you notice, at the end you've got these sealed off areas because you're doing a continuous extrusion. So the first thing that most biochemists do to the scaffold is cut, 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 and cut in order to expose more space in the scaffold. Of course, you could sort of go print, stop, and nowadays that's a reasonably reliable approach now. But even if you do that and you're playing around with the scaffold materials, you'll get stringing effects and things like that, which is not desirable. So, sorry, was the question? That's what I've just said. That's what I just said. You can, and nowadays the machines are better and more reliable, and therefore it's more possible. But if you're working with a material that you've not fully characterized, that you're extruding, so maybe you're working on the scaffold material itself, then when you stop, sometimes you'll get stringing. Okay? So you may end up with a bit of a mess. Okay? So if your build process is relatively reliable, then yes, you can. But even then, if you've noticed, when you stop, you usually get a swelling, yes? So if you get a swelling, you may still end up with a closing off of those pores. So, yeah, people are improving the technology all the time. There's now ways to even control the swelling effects by doing a suction technique at the end. It is possible. You name it. This is one of the points we're going to I'm going to talk about. There's all sorts of materials for these scaffolds. We've already mentioned quite a few of those. When the work that I was doing in Singapore, we concentrated on polycaprolactone. A lot of people are using polylactides, polyglycolides, PGAs, PLAs, PCLs, blends of all of the stuff, PLLA, which is quite a common material anyway for 3D printers. Basically a polymer which is sort of fairly organically constructed, is coming from usually from plant-based sources. A lot of these materials are coming from things like corn, but then also you can use celluloses. People are working on chitosan materials, which essentially come from shellfish sort of shells, chitin, essentially. You can also work with alginates. So these are also plant-based sort of materials. So there's a lot of different materials, and this is one of the areas that a lot of people are focusing on. What is the best scaffold material to use? Never mind how does it work with cells. You know, how does it function when you print it? Okay, so what I was basically leading on to in all of this is that there are multiple, the type of experiments and the type of products that we build with bioprinters usually involve a number of materials and maybe even a number of processes. So it's also quite common to have what you might, a version of a hybrid 3D printer. So up to now, we've thought of hybrid 3D printers as additive plus subtractive, yes? Here, it's broader than that because it might be additive plus then a surface treatment. It may be, which is maybe also additive. So it might be additive plus additive. It might be additive plus a chemical exposure. You know, you might want to expose it to UV light or something like that to sort of you know, kill the cells or whatever, to sterilize it before you do the next layer. There may be that you are additive, and we saw that with the heart thing, where you were actually had a hydrogel, a gel-like structure, and you were printing inside the gel. All of these things are very common in bioprinting experiments. So you ideally want a bioprinter that does that kind of thing. Okay, so and a lot of bioprinters now, that's what they do. If you look at this one, this isn't actually a bioprinter. This is just a highly versatile 3D printer. So this one, you've got extruders, you've got drill heads, you've got syringe heads. So what you do is you play around with your system, and you now look at quite a number of 3D printers that are on the market. It's quite common these days to have a 3D printer where you can swap the head out and put a laser on there, and therefore change it from a printer to an engraver or a cutter. You know, a laser cutter, laser engraver. You can also then swap it out and put a drill head on there. So these guys have just gone another couple of steps further by basically coming up with a variety of different heads. Some of these might be probes, where you can just measure stuff using the printer. So you can do like a coordinate measurement machine type device. This one, quite clearly, this is a syringe. This is the syringe holder. So you've got a little stepper motor drive system to drive the syringe to give a constant pressure or constant output. There's probably some other stuff in there. Maybe a camera, you know, all sorts of things that you could mount on a structure like this. This is not something that just is appropriate for a 3D printer. It can be all sorts of other devices as well. It could be a tape layer. I've seen some of those where you get you can lay down conductive tapes and therefore make PCB type devices. So this again leads on to embedding sort of electronics and actuators in there. So there's all sorts of things you can do with your printer. And so a lot of the bioprinter guys are buying machines like this because it's something they can easily use. I mean, I think the most important thing for bioprinting is, well, the two most important things. One is a conventional heat-based melt extrusion system for laying down usually low temperature or relatively low temperature polymers like PLAs. But then the other thing is a syringe-based delivery system. And then the other major advantage is the ability to switch between different delivery modes. So either a carousel type thing where you pick up the head, or you actually have multiple heads itself. So this is a carousel based. The previous one was a multiple head system. Oh, I have no idea with this machine, but I imagine it is, yes. And again, if you've got a hotbed, you don't have to use it, do you? If you haven't got a hotbed, then you haven't got a hotbed. So it really doesn't, you know, I mean, I don't know for this machine. I'm not that familiar with it. Right. For the types of materials they tend to use, they do not look to do the liquid to solid transformation quite so rapidly. So there are, for example, hydrogels which you dry out and they create a foam, solid foam. Yeah? You don't do that inside the machine. The usual practice is you create the structure and then you put it into a drying oven.
Here, the problem what we are facing is when you take it out and separately doing, contamination will be problem.
Sure. That's why you have a bio lab, isn't it? Contamination is a problem. Okay. Sure, yeah. Contamination is always a problem, but that's your life, isn't it? You know, you have lab facilities and you have protocols, and all your training is largely about avoiding contamination, isn't it? So why is this a particular problem when you're doing this all the time?
I mean, our application is not with respect to bio.
Aha, now we're getting to it, okay? So this is why you're not a biolab, because you don't really understand about protocols to maintain contamination. Where are our biochemists, bioengineers? Yeah, so you can talk, yeah, advise him on the best ways to avoid contaminations, okay? Yes? Yeah, I mean, I'm making fun of you, but the point is that yes, you're right, contamination can be a problem. It's always a problem. You can either, yes, have a delivery system in here which dries the scaffold out in situ, and maybe, yes, that does help, but there are other ways. And quite often, in fact, a lot of the drying methods don't actually involve ovens and stuff like that. They quite often involve, you know, immersion into weak acid solutions and things like that, to sort of more cause a cross-linking effect rather than a drying effect. And then you dry out afterwards. So there's a lot of different stages. One of the things that I learned from working, so I mean, I've had biochemists working for me in the area of tissue engineering, and the thing is that, you know, a lot of these, once I give them a scaffold, that's only the start of their work. And they spend a load of time. I mentioned about trimming off the scaffolds. Another thing is quite often you etch the scaffolds. So you might immerse into a weak acid solution, and that gives you a surface texture, which then will allow your coatings to be applied. The coatings are usually sort of an inorganic or non-bioactive coating, because it's sort of like an interface between the scaffold and then the active components like proteins, like bone morphogenic proteins. Even then there might be sugar coatings, which I was mentioning to you before, the use of heparin sulfate as a way to help those BMPs stay where they are. So, and then you apply cells, okay? And sometimes with the cells you're putting other stuff like heparin itself to help with the regenerative processes. So there's a lot of materials and a lot of different steps. And then that's it, you build your scaffolds, but then you do another set of experiments and to identify the cells. You know, you do all these ELISA tests and things like that, I mean, which are basically then identifying whether you've got living cells or dead cells, how many they are, whether they've integrated, and you do those over a number of days to then plot the growth coefficients. So it's complicated, all right? So if contamination, moving your part from the machine to somewhere else is a major problem, you're only on the start of the journey, okay? What's next? Yeah, so there's sort of like three approaches, if you like, or generic approaches towards tissue engineering. Some of these sort of relate to, so the three classics are biomimicry. I think you understand about biomimicry, yeah? You basically want to replicate some of the features of a biological system. When it says not functioning, this form, fit, shape, to me is also a bit to do with function. For example, we did some work in one of our design labs using, I'm trying to think what animal that we were trying to replicate. Basically trying to create a low friction surface which would then go on the bottom of skis, for skiers. So if you know how skis kind of work, you basically try to sort of create a low friction between the snow and the ski. Essentially, the compression actually causes the snow to melt slightly, and that causes a lubrication layer, which gives you the sliding effect. This could be more efficient if the surface itself was low friction. So we were looking at some animal designs and trying to recreate the shape of the animal skin on the base of the ski. And it didn't really work very well, but we tried. That is biomimicry. So this is kind of like what Dave means by not functioning is that it's not grown there. It's not grown into that shape. It's replicated using a conventional manufacturing method. We see a lot of these things. There's now a lot of sticky type of gripping type devices which are based around the use of newts and geckos and things like that, where a gecko actually climbs up a wall, not because he's creating suction, but because he or she is creating electrostatic force, attraction, because there's lots of very fine hairs on their feet. And so that gives you the traction. Anybody seen Mission Impossible 4? Yeah, where the guy climbs up the side of the Burj Khalifa in Dubai. Every time I watch that, I get vertigo. But yeah, that's the gloves that he's supposedly wearing, sort of electrostatic gloves, aren't they? Where you sort of slap on and then peel off, and that's basically how a lot of these kinds of devices work, and that's a biomimicry type of thing. Velcro is probably one of the first biomimicry products probably one of the most that was sort of kind of explicitly labeled as biomimicry, because the guy that invented Velcro saw that some of these plant seeds clung to fabric and the backs of animals and things like that as a way of plant dispersion. And it was because there's this little sort of hook mechanism. So that's kind of what we mean by biomimicry, and that's what we mean by we build it. We sort of understand the biomimicry effect and what it's supposed to achieve, and therefore build a device which has a similar effect. If anybody's a swimmer, follows the Olympics, the shark suit that was banned from the Olympics, that the Australian swimmers wore, that's the same sort of thing. It basically creates micro-turbulence. It's a textured surface. Everybody thinks that the best way to swim through water is to be as smooth as possible, until they found out that if you had a slight texture creating micro-vortices, then that creates a skin around you which allows you to go through the water quicker. So those kinds of things, understanding how nature has solved lots of problems in evolution. Okay, autonomous self-assembly. This is sort of like saying, okay, providing a mechanism for cells to build into multicellular and complex structures. So this is where a lot of the work is. This is where scaffolds live. Okay? Physical and chemical processes of tissue and organ development. In the last 10 minutes, I've talked to you and mentioned about how, when you've got a scaffold, how that leads eventually to a cellular structure. You know, and it's a multi-stage process. It's complicated, it's tedious, it's prone to error, and when you've got, as you increase the number of variables, you increase the number of options. So a lot of experimentation needs to be done. A lot of design of experimentation needs to be done in order to, you know, work your way through that minefield of options to come up with the best combination. And it also depends on your application. If you're wanting to make bones for experimentation, then your scaffolds don't have to be too complicated. If you want to make bones for implantation, then you have to think about the directionality of the bone, the trabecular structure of the bone, the fact that bones aren't a homogeneous structure, not even within the specific bone sort of segments. So cortical bone is not homogeneous either, certainly not in load-bearing conditions. You need to have that sort of fibrous structure. If you look at a branch of a tree, it's the same sort of thing. The fibers go lengthways. That helps with vascularization delivery of nutrients, etc., but it also gives you significant tensile strength, which allows for bending. So, you know, so you don't have, when you bend or apply a force which causes bending on your bones, they don't fracture. Okay? So, and think about how that corresponds to 3D printing. You know, if you're building a bone with an analog with 3D printing, the most likely is you build it exactly the wrong way round. Because you probably build it upwards so that you minimize support structures. And then you've got all those layers which are all fracture surfaces potentially. Yeah? So you know, these are the areas that we're working in. So we're basically encouraging the cell to build this itself and providing the most suitable accommodation that we can. Okay? And then organ engineering is essentially taking that one step further and realizing that, you know, this isn't biomimicry. Not really. It's functionality, it's biofunctionality, and so you combine the functionality with the actual structure, then you get organs. Okay? When I was looking at researching into bone tissue engineering, we spent a lot of time discussing and trying to understand osteochondrial effects, basically joints, cartilage, and bone. Okay? One of the things that we found is that we build our scaffolds. As I said, I mentioned we used PCL, polycaprolactone, as the polymer. But that's not very bioactive and not very bioinducive. Okay, it's biodegradable and reasonably inert, but it's not going to help too much in cell regeneration. So we used to mix the polycaprolactone with tricalcium phosphate. It's a bone ceramic, or bone analog ceramic. Similar sorts of properties to hydroxyapatite. So we mix those in, then we used to create our scaffolds, which was essentially a composite. Now, I mentioned about etching of the scaffold. One of the reasons that we use to etch the scaffold is because when we incorporate the calcium phosphate into the polymer, it goes into the middle of the polymer feed. So you end up with an extrusion. You extrude, okay, from the nozzle. So here's the nozzle, here's the extrudite. What happens is in the nozzle, you'll have particles of TCP extruding into the molten, or being carried by the molten PCL. And because of shear effects and shear turbulence in the channel, what you'd have is little micro vortices here, which basically allow you to extrude and provide the well, not here actually, here. This is outside of the nozzle. You would not get the particles at the surface of the scaffold. So the TCP might be bioactive, but it's no use because the cells don't see it. The cells won't detect it. So the first thing we would have had to do, and the first thing we did, is essentially dissolve our scaffold so that the particles are then exposed. And then, so we would have a smaller scaffold, pore sizes would be bigger, and those would then have the TCP powders there, and the cells would be able to bond with the powders. What was I also going to say? We've not mentioned the pore sizes very much yet. The scaffolds that we used to generate, we try to aim for a pore geometry of around about 500 microns, about half a millimeter, in sort of general dimension, overall dimension. Cells, bone cells, around about 50 microns as normally. And so that allows for a population of cells to occupy a pore, but without too much bridging across that pore. And then also a bit of space for nutrients to get there, to allow for the cells to join together and to become healthy. What next? Yes. So, in fact, research is carried on at all levels. I mean, people are working on just 3D printing of cells. So this is the bio-ink part. So people are putting cells into syringes and then extruding them, and you know, because that's a good way of controlling the delivery. So therefore knowing where those cells are actually going to be. I mentioned about osteochondrial implants, and I forgot to mention. So as I said, we build the bone using PCL with TCP. Cartilage doesn't want the calcium phosphate there. It doesn't like it. So in there, the most likely is the scaffolds that we were building were PCL material. And then, so what you would quite often have, so if you had like a jointed component, say imagine, okay, simplest one to remember is probably a femoral head, okay? Okay? So all this would be nice bone around here, and then you'd want cartilage around here. So you've got a cartilage region, and you've got a bone region. One could also then subdivide that you would have obviously cortical bone with trabecular structure, so make sure that it's all, when people are playing around with, in the bioreactors with the bone, and then actually putting mechanical stress on the cells. Some using sort of inductive fields, some actually doing mechanical compression of the cellular structures. There's quite a lot of evidence to suggest that's how trabeculae actually form. That if you're actually pushing the cells in a particular direction, they react by growing along that direction. Okay? And then you've got cancellous bone, spongy bone inside here. Okay? Certainly around this region, then, you've got a sort of an interface. Okay, so you've got that interfacial region, and so what we were also hypothesizing is that probably we could build a scaffold in a 3D printer, kind of like that, which would give us the sort of bone formation that we want. Probably then we'd still have to think about how do we cause it to load, particularly when you've got variable load path. Okay, So this is vertical, this is like this way. Should I then apply a force this way and the force this way in order to cause that? But that's a long, long way in the future. But what we were then looking at was how do we deal with this? So what we were then thinking is, in fact, that we would use curved layer printing so that we print normal to this surface with PCL. So that was the kind of approach that we were considering during that time. Does that make sense to people? Maybe. Okay. What next? Moving into, so the cellular components, I suppose, is about, sort of stem cell work, I guess, and getting them to form into different types of cells. Then there's research on actually printing of the cells themselves. Then there's the sort of the 3D printing of tissues, and then also people that are trying to 3D print organs. So this is really just to try and say, okay, how does this all turn in from one thing to the other? So there's lots of research going on. So, when whoever it was that asked me, what materials, it's very, very subjective thing. There's a lot of materials. So there are, it's some interesting things actually as well. I mentioned about, so this is from Atala, Wake Forest, that I mentioned earlier, that did a lot of work on the bladder. And if you think about it, this is quite a common thing. Essentially our geometry is largely defined by our skeleton. Okay? A lot of the other the soft cell structures are really defined, could be considered as flat surfaces then wrapped around that skeleton. So it's a bit like taking a piece of cloth which has the flexibility, but then sewing it into a three-dimensional structure. The physical support coming from the skeleton. So if you think about that, that's what Atala was realizing with regards to his work on the bladder. In fact, he created bladder tissue which was flat. And then he just worked out a method to cut it up and sew it together so as it formed a three-dimensional shape and functioned as a bladder. And he inserted it in pigs and it worked. So he grew a bladder in the lab. From what I understand, the tissue structure is quite straightforward and simple compared to many others. It's not a multicellular structure, so that's why he chose it. But then it was quite easy for him to then create. But it was a great demonstration of what can be done. And the similar thing we can see, if we've got vascular and bronchial tubes in us, airways and blood vessels, then these are tube structures. Also relatively straightforward in their basic structure. The complexity comes from the branching and the size variations. Okay, and therefore it becomes a network type of concept. And I've got one later. But we can deal with this kind of like at this level, if we've got the trachea and we can do some kind of, people have talked about stents, for example, and splints and things. That's where that comes from. Okay? Corneas, kidneys then obviously are another dimension above that, into much more complex multicellular structures with a lot of branching in there. Lungs would be the same, livers would be the same. Pancreas. What else? Okay, so structural complexity, sort of some idea there about starting off with something relatively simple structure, two-dimensional, which is skin, cartilage, which can then be formed over more complex geometric forms. Tubing structures, vascular, aortic, trachea, and then fully three-dimensional structures, which relates to things like kidneys. However, I said skins and that thing is relatively simple, but the reality is, again, is not. I mean, okay, the geometric form might be, we might be able to produce a sort of like an epidermal layer, but then to also include other factors in there, including the hair follicles, etc. And then we're turning what is initially looking like a two-dimensional problem into a highly three-dimensional problem. But this is the kind of level that we're working at the moment. We're really just still playing around with simple three-dimensional structures, trying to get good mechanical properties, but then predictable properties, adjustable properties, but even then we look at these are not really adjustable yet, because we've not changed the density of any of these forms or anything yet. And this is the kind of thing that we end up working with, is sort of these sort of cellular structures. So the scaffolds have now been infused with cells and other nutrients, etc., and now are creating cellular tissue, bone, for example. We could play around with some of these ideas to create the geometry. So, yeah, it'd be nice. We're working a lot with just basic prismatic structures, but it is possible to do something similar with conventional 3D printing to create more three-dimensional effects, sacrificial processes, similar to support structures, etc., which we could apply in contexts like this to create a very complex tree-like structure, where like these cell scaffolds which are aimed at trying to create lung tissue. Time to break there? Let's break there, okay? We'll carry on from there. I've got a few more on this yet. Okay, tea time.